11.6 Absolute convergence, ratio, and root tests. So first, let's talk about absolute convergence. So if a given series is sigma a sub n, we'll consider the series with the absolute value of a sub n, and that is the sum of the absolute value of the terms of the given series. So definition, we say that the series sigma a sub n is absolute convergent if the series of the absolute values, if the series, I should say, of absolute values, sigma absolute value a sub n is convergent. Note, now, if sigma a sub n is a series with positive terms only, then the absolute value of positive term is just a sub n. And in this case, absolute convergence is the same as just convergence. So it makes sense to talk about absolute convergence for non-positive terms. Example, sigma negative 1 to the n minus 1 over n squared. This is alternating series, so let's expand it. If n equals 1, we are going to have 1 over 1. If n equals 2, will be negative 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared, and so on. So it'll alternate the signs. Now, let's look at sigma of the absolute value, negative 1 n minus 1 over n squared. N is from 1 to infinity, and that is sigma of 1 over n squared, because negative 1 absolute value will be positive. So this is a familiar series. Let's expand it 1 plus 1 over 2 squared plus 1 over 3 squared plus so on. We can have the first term as well. So this is convergent. Why? Because it's a p-series with p equals to 2, which is greater than 1. Okay, therefore, the given series, which was sigma negative 1 n minus 1 over n squared, is absolute convergent. Okay, so we took the series with the absolute value and we showed that that is convergent because it's a p-series with p greater than 1. Then the given series is called absolute convergent. The reason is because this series with the absolute value was convergent. Example 2. Now we're looking at sigma, n from 1 to infinity, negative 1 to a power n minus 1 over n. Expand it, n equals 1, and we'll have 1 over 1. N equals 2 minus 1 over 2 plus 1/3 minus 1/4, and so on. This is familiar. We call this harmonic series. And if you remember, that was divergent. You can think about being the p-series with p equals 1, so it's divergent. Okay. So, what that means, here, we need to explore the absolute values now. So we have sigma absolute value -1 n minus 1 over n. Okay, so I need to make a correction here. So the harmonic series was without the absolute value. So we need to, this is not the harmonic, this is the alternating harmonic series. Okay, so this one is alternating harmonic series, not just a harmonic. And it is convergent. We showed that earlier. It is convergent, but not absolutely convergent. So the alternating harmonic series that is given is convergent, but not absolutely convergent, because if we look at the absolute value of the terms, -1 n minus 1 over n, that would be sigma 1 over n, which is 1 over 1 plus 1/2 plus 1/3. Now, this is the harmonic series, and that is divergent. So this is the harmonic series, and we know it's divergent. So the series with the absolute value was divergent. Therefore, the original series is not absolutely convergent, because the definition we had to have absolute convergence, you need the series of the absolute value to be convergent. And in our case, it was not. The series with the absolute value ended up being the harmonic series, which we know is divergent. So the original series is convergent. It is convergent, but not absolutely convergent. So let's give a definition now. Since we already have definition for absolute convergent, now we need a definition for a series that is conditionally convergent. Conditionally convergent. If it is convergent, but not absolutely convergent. So that means the series is convergent, but the series with the absolute value is not convergent. So we call this conditionally convergent. So that means convergent, but not absolutely convergent. So previous example with that series shows that it is conditionally convergent. A theorem: if sigma a sub n is absolutely convergent, that means the series with the absolute value is convergent, then, more space here, then it is convergent. Okay, so that means absolute convergence, absolute convergent applies convergent, but not the other way around. So the converse is not true. The converse is not true. In other words, if you have a convergent series, it may be absolutely or not. So example, determine whether the series is convergent or divergent. And here it is, sigma cosine n over n squared. So let's expand it. That's cosine of 1 over 1 squared plus cosine 2 over 2 squared plus cosine 3 over 3 squared plus, and so on. So this series has positive and negative terms. Now, we don't see the negative terms. They're kind of hidden because they're expressed in terms of cosine. But we know cosine could be positive or negative, right? Cosine is positive in the first quadrant, negative in the second quadrant. So depending on the value, at some point you have some negative terms, but these are not alternating. So this series has positive and negative terms, but not alternating. That means you have a bunch of positive, then a bunch of negative, then positive again. All right, so consider sigma of the absolute value, cosine n over n squared, n from 1 to infinity, and that is equal to sigma. I'm gonna only keep the absolute value to the numerator because n squared is always positive. Now, anytime you work with sine and cosine, keep in mind that they're bounded. So we know that the absolute value of cosine n, or cosine of anything, is less or equal than 1, and that's true for every n. Therefore, we can say cosine n, absolute value, over n squared is less or equal than, now substitute cosine n with 1, because that's the biggest it can be, so 1 over n squared. Now we know that the series of 1 over n squared is a p-series, and it's convergent, right? Because it's a p-series with p equals 2, which is greater than 1. Therefore, so we have we found a convergent series that's bigger than our absolute value. So by the comparison test, the absolute value of our terms here, this series is convergent by the comparison test. Okay, therefore, the original series, the given one, cosine n over n squared, that one is absolutely convergent. And by theorem 1 that we just wrote, it is also convergent. All right, so the question was to show it's convergent or divergent, and we actually show that it's absolutely convergent. In other words, we use the series with the absolute value, use the comparison test, and we prove that the series is absolutely convergent, and by the theorem, it is convergent. So 2 more tests, very important. First, the ratio test. All right, 3 situations. Number 1, if the limit of the ratio of the n plus 1 and the nth term, absolute value, n goes to infinity, if this limit is equal to L, and that L is a number less than 1, then our series is absolutely convergent, and therefore convergent by that theorem. The second situation, if the limit of the same ratio, n plus 1 over the nth term, absolute value, if that limit is equal to a number L that is greater than 1, or that limit is infinity, when n goes to infinity, then our series is divergent. And a third situation, when that limit is equal to exactly 1, so if the limit of the n plus 1 over the nth term, absolute value, if that limit is equal to 1, then the ratio test is inconclusive. That means we can't tell whether it's divergent or not. So we have this 3 situation, less than 1, we have absolute conversion, therefore convergent. If that limit is greater than 1, then we have divergent. If it's equal to 1, then we don't know. We have to use a different test. All right, example. Test the series sigma -1 to the nth power n to the third over 3 to the n. Test this for absolute convergence. We're going to use the ratio test. Let's write the nth term is -1 to the nth power, n to the third over 3 to the nth. And now make that ratio, and then we'll take the limit afterwards. Absolute value. So I'm going to do this. I'm going to actually divide them. We know what it means to divide. How about we do this? We multiply by the reciprocal. Right? So that is -1 to the nth power, n to the third over 3 to the n. And then, oh, no, we have to do the n plus 1 term first. So we're going to have -1 to n plus 1, n plus 1 to the third over 3 to the n plus 1. That's the n plus 1 term. And now I'm going to flip the nth term. So 3 to the n is on top, -1 to the n to the third right here. We can ignore the negative ones because we're talking about absolute value, n is positive. So we have n plus 1 to the third. I don't need the absolute value. And then we can cancel that later, 3 to the n here, and here 3 to the n plus 1, and here n to the third. So that's what's left. And we can cancel that 3 to the n with this. And what's going to be left here is just 3. So we're going to have 1/3 n plus 1 over n. Let's do this together to the third power, which is 1/3. 1 plus 1 over n to the third power. Now, we're doing the limit now, so let n goes to infinity, and that limit goes to 1/3, which is a number less than 1. So by the ratio test, the first part, the series is absolutely convergent and therefore convergent because the limit of this ratio is a number 1/3 less than 1. Another example, test for convergence of the series sigma n to the power n over n factorial n from 1 to infinity. So the nth term is n to the n factorial. It is positive, so we don't need to bother with absolute value. Make the ratio. And to avoid complex fraction, again, I'm going to use this to divide means to multiply by the reciprocal. So the n plus 1 term is n plus 1 to a power n plus 1 over n plus 1 factorial. And now I'm going to flip the nth term, and we have this. Now I can write, let's see, I can write n plus 1 to the, let's see what we can do here. Let's do this, n plus 1 times n plus 1 to the n, and here n factorial over, I'm going to write n plus 1 factorial as n factorial times n plus 1. All right, so what cancels? Obviously the factorial, the n plus 1, and what's left is n plus 1 to the n over n to the n. Write it together. So that is 1 plus 1 over n to the power n. And what happens when n goes to infinity? Take that limit. That goes to a famous number, Euler's constant E, and we know E is greater than 1, it's about 2.71. So the ratio gave us a number greater than 1, so by the ratio test, this is divergent. All right. So another test, which we use for nth powers, it's called the root test. So the root test, it's convenient to use if you have nth powers. The root test for nth powers. It has 3 cases as well. It's very similar to the ratio test. But if the limit of the nth root of the absolute value of the nth term is a number L less than 1, then the series is absolutely convergent. Our series is absolutely convergent and therefore convergent by that theorem. Second case, if the limit of the nth root of the absolute value of the nth term is some number L greater than 1, or that limit is infinity, then our series is divergent. And third case, if that limit is exactly 1, then just like before, then the root test is not conclusive, or it's inconclusive. That means you don't know. It could be convergent or divergent. You have to use another test. Note that the third case, if you get the third case in the root test, you get the same third case in the ratio test. So you have to use a different test. All right, example. Test the convergence of sigma 2n plus 3 over 3n plus 2 to the power n. Note you can do the ratio test. It's going to be a little bit easier to do the root test here, so and faster. The nth term, obviously, is 2n plus 3 over 3n plus 2 to the nth power. We're using the root test now, and we're going to take the nth root of the absolute value, which is always positive, so we don't need okay, do we need to show this? So nth root of 2n plus 3, 3n plus 2 to the power n. So the nth root and the n cancel. 2n plus 3 over 3n plus 2. This is not very clear. Let me do this one more time. Okay. So 2n plus 3 over 3n plus 2. Now let's divide by n, top and bottom, because that's how we find limit at infinity. Cancel. So you have 2 plus 3 over n, 3 plus 2 over n. So we know that goes to 0, that goes to 0 if n goes to infinity, and you have 2/3, which is a number less than 1. So we have absolute convergence, and therefore convergence by the root test. And that concludes this video.